is Sam Miranda. I am a retired nuclear engineer. I've been working in the private and public sectors for more than 40 years, where I specialized in nuclear safety analysis and design and licensing. And I understand that you want to talk about construction. I can address some of the aspects of construction, and I can tell you that building a nuclear power plant is quite different from other projects. Are we ready to begin?
Yes, we are. Sam, go ahead, stand up.
Okay. This is a aerial view of a nuclear power plant in Maryland, Calvert Cliffs. And you can see here the key components of what we call a nuclear island. These are the containment buildings. There are 2 units here, 2 containment buildings, 2 reactors that are inside these buildings. And in here we have the turbine building, turbine generator building. And what you see here is water flowing out into the ocean. This is the cooling water before the turbine generator, actually. And it's not radioactive, it's just hot. And this is one way that a nuclear plant will reject heat. That it's used the water here. It's not good anymore, so it's spilled out into the bay, and fresh water is sucked in to continue the generation process. Here's another picture. This happens to be 3 Mile Island in Harrisburg, Pennsylvania. And this is the other way that nuclear plants will reject heat. They have these cooling towers. And this is water vapor. This is that hot water, but it's evaporated into the atmosphere. It's not radioactive either. And here are the 2 containment buildings. And inside you have the reactors. And then in between, you have the turbine generator units. And these structures here are the intakes from the river for cooling water. This is an old picture. This is the first commercial nuclear plant in the United States. This is a construction photo of the shipping port plant in Beaver Valley, Pennsylvania, shipping port, Pennsylvania. This is Western Pennsylvania, and you don't see a whole lot here. This was the first reactor that went into operation in the U.S. It began operation in 1957. And this is a photo of construction probably around 1950. The first reactor, for your information, was a surplus propulsion reactor from an aircraft carrier that the Navy didn't want. So they converted that into a power reactor to supply electricity to the people of Western Pennsylvania. So this is the process, and I think you'll get an idea of what I mean by construction of a nuclear plant is quite different. This is the containment building, and inside, this is the reactor. There's a pressure vessel in here. And these 2 things here are steam generators. They're there for the purpose of boiling water. And the resulting steam comes out through these pipes into a turbine generator. These are the turbine generator blades. They spin as the steam goes through the blades, and they turn the generator, which generates electricity. And meanwhile, the steam continues through and gets condensed here. And then the condensed steam, or actually it's hot water by now, it goes into the cooling tower where it's evaporated into water vapor out here. And the electricity is out here. Now, some aspects of nuclear power plant construction that might be relevant are this part right here, the reactor vessel. It contains water at a very high pressure, about 2250 psi. What that means is that, 2250 psi is about the pressure, 9 or 10 times the pressure that you would develop inside a steam locomotive. So why does the pressure have to be that high? After all, you just want to generate steam to turn a turbine here. Well, the thing about heat transfer is it always goes from hot to cold. So whatever water you pump into these steam generators has to be hotter than the boiling point of the water that's going to be turned into steam, that's going to turn the turbine generator. And you want pressure. You want a good high steam pressure. In this case, it's about 1,000 psi. So if you pressurize the water, you raise the boiling point. So here you have very high pressure water, 2,250 psi, which means the boiling point of this water is around 650 degrees Fahrenheit. And then the boiling point of the water inside the steam generators, it has to be lower than that. It turns out it's about 550 or about 100 degrees lower. So here you have water boiling at about 550 degrees and producing steam pressure here at about 1,000 psi, pounds per square inch. So that's how that works. So what that means is this reactor vessel has to be very strong. It has steel walls about 6 inches thick or more, and these things are very, very hard to produce. There were only a couple of companies in the U.S. that were capable of producing reactor vessels like that. One was Babcock and Wilcox. Another one was Chicago Bridge and Iron, and so on. That ability, by the way, has been lost. Today, if you want to build a new nuclear plant in the United States, you would have to import one of these reactor vessels from Korea or Japan. This containment building is also, it's not just a building, it's a system in itself. These walls are about 5 or 6 feet thick, and they're concrete, and there's a steel liner inside. And the purpose of this building is to contain any steam that might be released from this reactor vessel in case of an accident. That highly pressurized water, if it escapes the reactor vessel, it's going to flash into steam. And that steam is going to pressurize the inside of this containment building, and that steam is going to be radioactive. So it's important not to allow any of this steam to get out into the atmosphere. So this containment building here is capable of withstanding pressures of about 50 psi. And is tested regularly for leakness.
Oh, I saw that y'all use uranium fuel cells for the steam process with the nuclear engineering. How's its reusability, and what do y'all how do y'all dispose of it after it's gone through its lifespan?
The fuel cells, these are in the core. You have these fuel rods, and after they have been used usually for about a year, they're replaced. There are people looking at the possibility of reusing them. There's some very advanced reactor designs, but they don't exist right now. And in the United States, the law says that these spent fuel rods, that's what they're called, that they're highly radioactive, have to be stored. They cannot be reprocessed. The original idea when nuclear power came into existence back in the 50s was to reprocess the fuel and extract from them plutonium, which is made as part of the fission process. You can use the plutonium to build new fuel rods and use them again in the reactor. But this is not done in the United States. Other countries reprocess fuel rods, in France, for example, and Japan, but not in the U.S. That law was passed during the Carter administration, and it was for the purpose of making it very difficult it was non-proliferation concerns, actually. It was to keep the plutonium locked up in the spent fuel rods so they could not be diverted into making nuclear weapons. Okay, so here's another. This is a different design of reactor. This one doesn't have steam generators. This is called a boiling water reactor, but the same principle. Here the water is boiled inside the reactor vessel. This vessel is at a lower pressure. It's at 1500 psi, but still hot enough to produce steam at high pressure at 1000 psi to turn the turbine generator. And then that steam is condensed here. And it's condensed here actually. But here's the containment wall. It's about 5 feet thick, and there's a steel liner inside. The wall's made of concrete and steel, and it's designed to contain this 50 psi pressure. What is not shown here is that the containments also have pressure suppression devices. Like in this case, this containment would probably have a spray system up here that would spray it would be like a fire sprinkler system. It would sprinkle water into this building to condense the steam if there is an accident that releases steam. So this is an illustration of a containment building that has the steam generators. There's an overhead crane here. This is used mainly for moving fuel rods in and out of the reactor vessel. Here are the reactor coolant pumps, which pump cold water into the reactor vessel, and the hot water comes out of the reactor vessel after it goes through the core, past the fuel rods, and into the steam generators, where it transfers its heat into the water that resides inside the steam generators, and it's there for the purpose of boiling into steam, and then the steam comes out through these pipes into the turbine generator. There's the steel liner right here, and there's the containment spray that I mentioned before that will, in case of an accident, will spray cold water into the containment and condense any steam that comes out of a break in a pipe, for example, in the cooling system here. Here is what a reactor vessel looks like. This is the shipping port vessel. Again, this picture was taken in 1950. It's a small vessel. This is that aircraft carrier reactor that I mentioned. So this is a small vessel, but you can see how big it is when you compare it to the size of the people standing around. These are the inlets and outlets of the cooling water, also here and here. This is another vessel, a more modern vessel. It's bigger. And again, you can see how big it is when you compare it to the people walking alongside the truck. And this is the containment building that it's going to go into. It's being transported to the containment building during the construction of this reactor. This one's in Maryland. Here it is going into the containment building. So that's how they put it in. They'll mount it in there. And by the way, these components are so heavy, they're so hard to make. I mean, there are reactor power programs in other countries, and I'm thinking about Russia, which didn't have the ability to make these heavy forged parts like reactor vessels. So they adopted a different design of reactors that did not require a reactor vessel. They just used concrete, and that was called the RBNK design, which is the design that was used by Chernobyl. And that had other problems, as you're probably aware.
We have a question.
Okay.
How much do those vessels typically weigh?
I don't know. You know what? I never really thought about that. I can tell you that they are about more than 20 feet high. The vessel walls are 6 or 8 inches thick, and it's a big difference between whether you weigh that vessel empty, devoid of there are lots of internal parts. for example, supports for the fuel rods themselves. The fuel rods inside the vessel weigh about 500,000 pounds. That number I'm familiar with because I needed to use that number in my analyses. I was not really concerned with the weight of the vessel because that vessel is not supposed to move. Actually, it's mounted on seismic snubbers, by the way. In case of an earthquake, these are like big springs, so that in case the ground moves, the vessel will remain in place and it will not put a lot of strain on the connecting pipes and cause a pipe to break. About all I can say in answer to your question is it's very heavy. This is a piece of construction history. This is an old construction schedule for a reactor. This dates back to 1973. A more recent construction schedule, I don't think you want to look at it. It's pages and pages long. This is a very, very simplified construction schedule. What it does tell you, though, is that it takes about 7.5 years. This is the beginning. This is the beginning right here, the contract award at minus 7.5, and this is 0. This is when the reactor actually begins operation. So from the contract award to operation is about 7.5 years, and this is an optimistic schedule. They often take a lot longer than that. The fastest schedule of any plant was a plant in Louisiana, and that one was built in 6 years. For comparison, this is a nuclear plant back in 73. For comparison, if a utility wanted to build a coal-fired plant to produce the same amount of power, a coal-fired plant would take about 6 years. This schedule, by the way, got longer. There's an additional 2 years that you have to consider to produce an environmental impact statement. So that's one of the first things you do when you build a new nuclear plant. You get a permit for the site, for the land on which you want to locate your reactor buildings. And you also need to do an environmental impact statement, which covers a lot more than the site. It covers the surrounding community, emission concerns, radiation, exclusion zone, effects upon the population and the economy. It takes about 2 years to produce a comprehensive environmental impact statement, and that's before you can do any building.
We have another question.
Okay.
His question is, does this job that you were doing take you out of the country?
Yeah, it has taken me out of the country on occasion. I worked in Brussels and Madrid for a few months, also in Italy and Japan and South America. I was also involved in some international panels and committees in Vienna. I would say I don't consider that going out of country very often. I went out of country as necessary. Whenever I was working on international projects, or the work in Austria and Vienna was with the International Atomic Energy Agency, which was writing new standards for nuclear plant design and analysis. And I was one of the people on a panel that was writing those standards.
Are you familiar with how many power plants are in use in the U.S. today?
That is a well-known number. Right now it's 99 reactors that are operating. It was as high at one time a few years ago, maybe 5 years ago. It was up to about 107 reactors. They are, some of these reactors are being shut down. I think 6 reactors are scheduled for shutdown within the next 5 years. What's going on in the U.S. right now is there are no new nuclear plants being built. There are 4 that were started in South Carolina and Georgia. The 2 in South Carolina advanced reactors, safer than the current generation. They're new reactors, but they have been canceled. The financing was not did not make it feasible to continue building those. The ones in Georgia are also in trouble. So there are 4 plants in the U.S. that were started, but it does not look like they'll go into operation. Meanwhile, the utilities want to get as much use out of the reactors they have that are operating. So they're going to the NRC and asking for extensions on their licenses. These plants are licensed to operate for 40 years, and they're asking the NRC to allow them to continue operating these plants for another 20 years. And in one case, they've already asked for an additional 20 years. So there are 2 plants in Florida that are authorized, that will be authorized to operate for a total of 80 years. Personally, I don't agree with that. It gets very risky when you operate plants. I believe it gets very risky to operate plants that beyond their design operating lifetimes. And you can look at it in terms of your own personal experience. I mean, how long do you want to operate a car? After some time, it's time to get a new car. Or, can you imagine running your old? It's a beautiful. Suppose you have a beautiful antique radio in a walnut case in your living room, and it has vacuum tubes. Imagine getting a new vacuum tube when the old one burns out. Anyway, so the answer to your question is today there are 99 plants in operation, and that number is expected to get smaller rather than larger. On the other hand, India just announced that they're going to build 21 new reactors. China is building another 27. So the new construction of newer, more advanced reactor designs is going on overseas, not in the U.S.
Her question is coal, or which is cleaner, coal or nuclear power plant?
Nuclear power, when it was first proposed back in the 50s, was supposed to produce electricity that was too cheap to meter. And that was based upon the notion that they were going to reuse the fuel, that a nuclear power plant would actually produce more fuel than it burned, because the spent fuel rods would be removed and the plutonium would be extracted and made into new fuel rods and then put back into the reactor. And this could go on and on and on, so that the source of heat to generate the steam would be free, basically. And then that didn't work out that way because the American companies were prohibited from doing that by law. And then the environmental movement came into prominence in the 70s and 80s, and now nuclear plants they're not being promoted as too cheap, producing power that is too cheap to meter. They are being promoted as clean energy because there are no carbon emissions from nuclear power plants. Coal plants will always be generating carbon dioxide and other things, and nitrous oxide that pollute the atmosphere. And there are things you can do to scrub that and make it cleaner, but it's not going to be zero. With nuclear power plants, that number is zero. So yes, nuclear power plants are cleaner than coal. They were talking about reducing the construction schedules. So currently, this construction schedule is somewhere between 9 and 10 years. The previous slide I showed was about 7.5 years. There's a good part of that is construction, but there's also a lot of work involved in the beginning before you can begin construction, in the environmental impact statement, for example, and preparation of the site and getting the plant licensed. CP review means construction permit review. You have to get a construction permit, and then OL review, that's the operating license. And they've changed the system, by the way. Now you get just one license. These two are combined. But they were trying to reduce the schedule by using standardized plants. And these are plants that you would buy off the shelf. They would all have the same design, so that reviewing the design is much shorter. See, this is much shorter than that. To continue with that process, they would shorten the construction schedule even more by using standardized plants on designated sites. So, what that means is that the sites upon which you build the plants would also be licensed ahead of time, so they would not part of the what we would call the critical path that would extend the construction time. And that's what nuclear utilities are doing these days too. Any nuclear utility operator who wants to build a new plant will generally choose a site that is already licensed for a nuclear power plant. So they might have a few acres of land where they have maybe 2 reactors operating on that site. They would go to the NRC and would say, well, we want to add another 2 to the same site. They just build them alongside. And that has the advantage of the site is already licensed. It's already approved for a nuclear power plant.
Are you familiar with any nuclear power plants in South Texas?
The nuclear power, I've been to them. Those are Westinghouse plants, and they are very large plants. They're the largest plants that were built in the U.S. They've been operating for some time now. What did you want to know about them?
With other nuclear power plants in other countries?
They used to be the largest nuclear plants in the world, but that's not true anymore. Other countries are building larger plants. Combustion engineering has a design for larger plants. And also the Koreans have a design for larger plants. So compared to the new reactors that are being built in Korea, for example, they are about average. They are about the same size.
Where do we get the fuel rods?
Where do we get the fuel rods? Okay. The fuel rods are about a little bit, they're thin, they're about a little bit thicker than a pencil, and basically they're tubes of a zirconium alloy. They use a zirconium alloy because zirconium does not absorb neutrons as much as stainless steel. The first nuclear plants back in the 50s used stainless steel. Now they use zirconium, which has other problems. Inside the fuel rods, there are pellets of a ceramic, which is uranium dioxide. And the uranium dioxide is manufactured in the United States. They're manufactured by Westinghouse. There are other manufacturers as well overseas. But what happens is the uranium is mined, and then it needs to be enriched. And they do this by converting it into yellow cake, which is a powder, a yellow powder, which and then it's gasified. And the gases are sent through centrifuges, and you might have heard of these because the Iranians have been building a lot of these centrifuges, and they separate out the uranium-238 from the uranium-235. The uranium-235 is the isotope that fissions. The uranium-238 is not useful in a nuclear reactor unless you want to create plutonium. But in the U.S., plutonium is not something that they want. Anyway, they do this by using the difference in weight between the uranium-235 and the uranium-238 to spin it through. They spin the gas through a centrifuge, and the uranium-238 goes to the outside, and the uranium-235 stays closer to the center. They separate the uranium-235, and then they centrifuge it again, and they do it again and again and again until they get the desired enrichment, which means that the uranium that is mined, the natural uranium, the amount of uranium-235 is only about 0.3% or something like that, and they get that up to about 2.7 or 3%. And that is what is used in the nuclear reactor. So the answer to your question is the rods are supplied by companies like Westinghouse, and they're made, by the way, in Columbia, South Carolina.
So you said that a lot of nuclear power plants are going out of service. Does that mean the nuclear engineering job is kind of fading away with it, or is there still a need for nuclear engineering?
I would not advise you to go into nuclear engineering. There hasn't been a new nuclear plant ordered in the United States since 1978, with the exception of the 4 plants that I mentioned in South Carolina and Georgia, which seem to be at a standstill. But on the other hand, nuclear engineering has a lot of cross-disciplinary advantages. To be a nuclear engineer, you need to know something about electrical engineering, mechanical engineering, chemical engineering, mathematics, as well as